Hey guys, in this video I will be discussing as promised a few complicated variances from the second chapter of the syllabus. So I had left out a few complicated variances there. The derivations were a bit tricky, not really very tricky but a bit tricky. So, and these are not very important topics, but since they form a part of the core reading material, I did not want to skip anything. Okay, so we are going to do 2 to 3 derivations here, and you will realize that all of those derivations are actually very much related. And why did I take this topic separately? Okay, so the first thing I want to discuss with you guys is the variance of the present value random variable of a guaranteed annuity payable in advance. Okay, so this is what we are going to discuss, the variance of a present value of a guaranteed annuity that is payable in advance. So let me remind you what kind of a contract this is. If I make a number line timeline here, a guaranteed annuity basically says that there are n guaranteed payments going from time 0 to time n, all payable in advance. So the last payment is obviously at time n minus 1, and all these n payments are guaranteed. Okay, and after that the payments are payable as long as life aged x survives. Okay, so this kind of a contract takes place here. So if I talk about the present value random variable of such a contract, it is obviously it is a due kx plus 1 after this time, after n, so when kx is greater than equal to n, and it is a due n when kx is less than n, right? So that is what the contract is. Okay, so if I want to write this in form of a single notation, this can be written as a due maximum of maximum of um, kx plus 1 comma n, because we are taking whatever is maximum here, right? So this is how I can actually write this in terms of this. So this is a due maximum of kx plus 1 comma n, because when n is greater we are taking an, and when kx is greater than greater we are taking kx plus 1, right? So that is how it functions. Now let's just find the variance. Okay, variance of the PVRV is basically equal to the variance of a due maximum of kx plus 1 comma n, right? This is what I have here. Now let's just open this up using the standard formula for annuities. So this is the variance of 1 minus v to the power of maximum of kx plus 1 comma n. Okay, so this is what I have, and over d, right? So the d comes outside, and since variance is independent of origin, it becomes variance of v to the power of maximum of kx plus 1 comma n, right? Okay, now the challenge remains is only to calculate this part. So I'll just take this 1 over d square. This is the expectation of, I'm writing it as expectation of x square minus expectation of x whole square. So this is the expectation of v to the power of 2 times maximum of kx plus 1 comma n, right? Minus expectation of v to the power of maximum of kx plus 1 comma n whole square, right? Now the only thing I need to do is evaluate these. I need to evaluate both of these. So I'm going to start by doing this, and then I'll somehow find a relation between this and this, so get the whole thing. So the expectation of v to the power of maximum of kx plus 1 comma n is basically equal to, this thing is basically equal to, it's the, if I try to find it, if I write the present value random variable for this thing, so all this is saying is v to the power of maximum of kx plus 1 comma n, right? So that is just v to the power of kx plus 1, um, when kx is greater than or equal to n, and when kx is less than n, it is v to the power of n, right? That is what it is. Now if I need to find this, this can be written as basically the sum of going from, when we are less than n, so going from k is equal to 0 to, um, 0 to n minus 1, right? V to the power of n into obviously the probability of kx equal to, being equal to k, that is n, that is k deferred qx, right? Plus this part is going from n to infinity, right? Equal to, greater than equal to n means n to infinity, so that is k is equal to n to infinity, and v to the power of k plus 1 into k deferred qx again, right? The same thing. So let's just expand this. This vn comes out, so vn is out, and I've got a k going from 0 to n minus 1 k deferred qx, and this part is, it is just k going from n to infinity v to the power of k plus 1 into k deferred qx. So now if I look at these two, if I really focus on them, see what's happening here is you have got this part. Okay, this is saying that k deferred qx, where k is going from uh, 0 to n minus 1. So all this is saying is that the probability that the person dies in the zeroth year, that is between time 0, because this is the probability of surviving for k years and then dying. So this is saying that either the person dies between time 0 and 1, or he dies, or because there are additions, these are all summed together, so or he dies between time 1 and 2, or he dies between 2 and 3. In probability we know that summations mean or. Okay, so or he dies between time 3 and 4, going up till the probability that he dies between time n minus 1 and n. Okay, so this is basically the probability that the person dies between time 0 and n. All these mutually exclusive and exhaustive outcomes added together, so this just becomes v to the power of n into nqx, that is the probability that the person aged x dies within the next 10 years, plus k goes from n to infinity v to the power of k plus 1 into k def k deferred qx, is it? Yeah, k deferred qx. Okay. So if I look at this part of the expression now, this is saying going from n to infinity v to the power of k plus 1 k deferred qx. If you check it properly, this was the definition of uh, n deferred ax. This was the very definition of n deferred ax, that is the expected present value of a deferred annuity. So I can write this like this, and I have my answer here, right? Now I'll just put it into that definition and give you a proper answer. So this part, it just becomes 1 over, excuse me, just let me evaluate another thing too. Okay, so what this is expectation of v to the power of maximum of kx plus 1 comma n, right? That is what this is. If I want the expectation of, if I want the expectation of v to the power of 2 times maximum of kx plus 1 comma n, obviously this can be evaluated easily. This just becomes v to the power of 2n. nqx remains as it is because probabilities don't square up, and this term, it becomes n deferred 2ax, that is it would be calculated at the squared interest rate. So our final answer for the variance is basically equal to 1 over d square into v to the power of 2n into nqx plus n deferred 2ax minus this thing squared. So I've got a v to the power of n into n qx into plus n deferred ax, and this whole thing squared up, and this is my final answer for the variance of the expected present value of a guaranteed annuity that's guaranteed for n years to a life aged X, payable in advance. Okay, so this is your answer. And if I talk about the arrears one, so that is the variance of the present value of um, an annuity, a guaranteed annuity. So a guaranteed annuity payable in arrears. Now it's the same thing except for the part that the payments are happening at the end of the years. So if I draw the number line, see the payments are happening at time 1, time 2, time 3, going up till time n. The last payment would be at n, and hereafter all these payments are guaranteed, and hereafter the payments are basically they are basically dependent upon the survival of a life, right? So if I write the present value random variable, it is basically it is basically a n. Okay, it's a n. If the person aged x, that is kx, is less than n, right? So it's this, and if the person survives beyond this time, it is just a kx, right? Not akx plus 1, but just akx, because basically this is payable in arrears, and that one extra payment doesn't happen here. So it's akx when kx is greater than equal to n, right? So if I write this in one single notation, it's just um, a maximum of kx comma n, right? This is what I have here. Now there here comes a bit of an adjustment. Okay, I can write this as a due maximum of kx plus 1 comma n plus 1, right? Minus 1. I can actually transform this into this form, and I've already taught you this before, that the only difference between these two payments is the payment at time 1 at time n. Okay, so in order to adjust the payment at time n, I have made an adjustment here, and I've deducted 1. You should go back and check the annuities chapter again if you don't understand this adjustment, because I've explained this before also. And if you still don't, call me up or message me. Okay, I'll explain it again. So variance of a due maximum of kx plus 1 comma n plus 1, okay, minus 1, just minus 1 will actually go away because variance is independent of origin, so it goes away. And this is what I have for a guaranteed annuity payable in arrears. Now I have to simplify this. Now I can use the fact from the last part and just simplify it directly using the fact that I've got a k plus 1 similar to before. It's just that instead of n, I've got an n plus 1 here. So I can just adjust the last formula to get my answer. So I had this formula in the last part. So if I want one for the annuity payable in arrears, so the variance just becomes 1 over d square into v to the power of 2. Now n, instead of n, I've got an n plus 1 here. If you observe this carefully, see, I've just got an n plus 1, except for that everything else is same, and this 1 goes away because obviously variance is just independent of scale, so it just goes away. Okay, I'm going to delete this. Okay, so it went away, right? It went away. So I've just got a n plus 1 in place of n as compared to the last part. You can go up and check it too. And so the answer just becomes very simply, I just have to replace this n with n plus 1. So this becomes into n plus 1 qx plus n plus 1 deferred 2ax. let's erase this part. In fact, I'm going to erase the entire thing. Okay, I'm erasing this so that I can write the formula more clearly for you guys. Okay, I'm going to write it more clearly now with a different colored pen so that it is very clear. So the variance for a guaranteed annuity payable and arrears is just 1 over d square. Now replace n plus 1 in place of n in this equation. So it's v to the power of 2n plus 1 into n plus 1 qx plus n plus 1 deferred 2ax minus again replace n with n plus 1, so it is just v to the power of n plus 1 into n plus 1 qx plus n plus 1 ax deferred obviously, and this whole thing squared up, and this is your answer. Okay, so this is how you do it in case of arrears. Now I'm going to move on to the next part where I am going to evaluate the variance of the EPV of a deferred annuity. Okay, that is what I'm going to do. Variance of the PV. I'm sorry, not the EPV, the PV. Okay, so I'm going to do it for a deferred annuity due. So a due. So how do I go about this? See, again, a number line for you guys. Time n times 0. See, what is happening here is I actually have an annuity that is going to start payment at time n. Okay, so before, if the person dies here, no payments. Okay, and it's gonna pay as long as the person aged x survives. Okay, so the payments only start at time n. So if I write the present value random variable, it is just v to the power of it's just 0. I'm sorry. Okay, yeah. So the PV is 0 when kx is less than n. Okay, when the person dies before time n, there is no payment. If he dies after time n, it is basically, I'm talking about the one in payable in advance. Okay, so it is basically a due kx plus 1 minus n. Okay, it is basically kx plus 1 minus n because there had been I don't know, there had been kx, there would have been kx plus 1 payments if this would have started at time 0, but since this is starting at time n, the payments are reduced by n, and this is multiplied by Vn. Okay, this is if kx is greater than equal to n. So this is, and if you want, and this is multiplied by Vn for the fact that I need to discount all these payments back to time 0, right? So therefore there is this Vn factor which you need to understand, and this we had discussed earlier too. So if you don't get it, you can go back and check again. Okay, so this is what we have here. So if I want to find the variance of this thing, variance of, if I want to write this as a single notation, okay, if I write this as a single notation, this can be written as a due maximum of, if I write this part as a due 0, because a due 0 is just 0, I'm writing this as a due 0, a due maximum of kx plus 1 minus n comma 0. Okay, so I can just write it as the maximum of these two. So this is the variance of A due maximum of kx plus 1 minus n comma 0, right? And if I evaluate this, up, this is just the variance of um, into Vn. Obviously, there will be a Vn here. I'm sorry, got to write that Vn because it's a Vn here. So the variance of this thing would be Vn into 1 minus v to the power of maximum of kx plus 1 minus n comma 0, right? This is what I have here, divided by d. Okay, let's just evaluate this. This is the variance of, if I multiply the Vn inside, it becomes Vn. For these two, if I multiply it here, it becomes minus V maximum of, I'm multiplying v to the power of n here. So n adds in kx plus 1 minus n, so it just becomes kx plus 1, and with 0 it becomes n. Okay, so this is what you have here, minus upon d. Okay, now the way ahead is very simple. Okay, d comes out, it becomes 1 over d square. This is obviously independent of any constant, so it becomes v to the power of maximum of v to the power of kx plus 1 comma n. Now you must have noticed something really beautiful here, and if you couldn't, I am going to tell it to you. This is basically the same as the variance of a guaranteed annuity payable in advance. You can turn back your pages and see. So in a very similar way, I can also write this formula like I did in terms of in case of a guaranteed annuity payable in advance. So this just becomes 1 over d square into Vn into nqx plus, again this is 2Vn, 2 v to the power of 2n obviously, because this is the square term, n deferred 2ax minus uh, v to the power of n into nqx plus n deferred ax, and this entire thing whole squared, and this is your formula. Okay, but in your book they have done an adjustment here. Okay, and it's a pointless adjustment. I don't even know why they did it, but they have done it, so I'm going to give you answer in that form. What they did here was they just wrote this as 1 over d square. They wrote this part as v to the power of 2n into nqx. This stays the same. They've opened up the formula for a deferred annuity. Okay, so they have written this in terms of a whole life annuity. They've written this as v to the power of 2n into npx. Okay, this becomes v to the power of 2n into npx into a 2ax plus n. Okay, so that is what it becomes. It just they have just multiplied this deferment factor and then written it in form of a whole life annuity, and we have used this formula earlier too. Okay, minus v to the power of n into nqx. Again they have done the same thing with this part too. They have written this as v to the power of n into npx into ax plus n, and again this thing whole squared, and this closes up. Okay, the next thing they did was they took out of this entire expression, they took v to the power of 2n common. Okay, so v to the power of 2n upon d square, and this I've got nqx plus npx into, this stays the same, 2ax plus n. I just took out v to the power of 2n common out of this, minus we take as this whole thing is squared, we can, if we take v to the power of n out, it becomes v to the power of 2n. Okay, uh, naturally. So this is just nqx and plus npx into ax plus n. So yeah, they have written this formula in this form, but you don't need to. There is actually no point to this. Okay, there is really no point. And I think that's all for this video, guys. And I hope you enjoyed it, and thank you. And this is all about these variances, and we are done with the first three chapters now. That was everything that was in the first three chapters. So start doing your revision notes, and I think that's what you need to do. Talking about these variances, they were a bit complicated formulas and derivations, so you can even skip them. They are not very frequently asked in the exams, but I would, you can skip them, but I would suggest you to do them because I don't know, they form a part of your core reading, and I don't think you should skip anything. And these topics are really interesting, although they are tricky.